So the first thing today that I wanted to cover were the assignments that the sketching assignments. All right. So let me find that sheet. It was 2.5 was the first one. It's this guy right here. Right. So this is 2.5 number one, and this one's really pretty simple. I can't even think of anything that's too difficult in this one. I guess something that might be a little tricky. Let me get my pointer working here real quick. One pointer. That right in here you have a hidden line, and you have one on the opposite side. But this line here and here, those are center lines, and so there should actually be a little visible gap inside there. Sometimes when I try to enlarge these PDFs, I lose that definition, but hopefully you caught that. That would be one thing you would want. And the other thing, be sure that you ran that hidden line through right there for this crease that's right up there. Okay. So I'm going to go through these quickly so we can get onto the CAD stuff, but if you have a question, feel free to unmute and ask me a question, and or put it in chat. I'll also check the chat window occasionally. All right, so this one, we have a couple of oblique planes, and really the only way to identify where those planes are is to find the grid point and find the corresponding grid point and just connect the dots. So hopefully you were able, from counting grids up in here, to figure out, where those would be. And so like the length of this line right here, and on the opposite side over there, that's a half grid. So right here, that's a half grid, and then this is a full grid, and so we connect that, and that's how we get this edge in. Pardon me. And then of course we see this. So while this is an oblique plane, and this is an oblique plane here, really the only thing we can do is connect the dots on those. Now, the other day I told you guys that an inclined plane, the way you know it's inclined is that it will appear as an edge view in one of the 6 regular views. So the 6 regular views are front, top, bottom, right, left, and rear view, or back view. But an oblique plane, which will be like this guy here, these guys up here, they never appear as an edge view in the 6 regular views. You would have to create an extra view called an auxiliary view, and that would be the only way you could get your line of sight normal to that oblique plane. And remember, if you're normal to it, you're perpendicular to it, and at that point you could see it in true size and true shape. All right. So anyway, hopefully you were able to, piece all those oblique planes together. This guy, what you want to watch out for, I guess, is that you have a concentric cylinder that you see as a hidden line here, and then you have an arc, and you want to extend those center lines out a 1/4 inch past the edge of the arc, because those are concentric right in there. All right. And then you have this hidden line here, which projects from the quadrant right here of this guy. Now the other thing that you want to watch out for in the top view is, you see this plane that you have right here in the edge in the front view, which represents that area right in there on your isometric drawing. That gives you a visible line right there, and so that needs to project straight up from this plane here, and then it goes into this arc, and that arc runs out. Okay, so the other day I think I mentioned that a run out is where you don't have an edge, it just blends in. And so what happens in your top view is you won't have a visible line in the top view for the run out, but you do have a center axis for this round shape that you have here. So that's what you're seeing right here. That's a center line, and this is a center line up there. Okay. All right, so here we have a stadium that's actually a cutout. So it goes all the way through the part. So we expect to see hidden lines here and hidden lines here for the quadrants of the stadium where that would project up, right? And then we'll have a center line for the center axis, and these are concentric. The ends of the stadia, I guess that's the plural, are projecting up there. And then we have this notch, and the notch goes through both sides. So we need hidden lines in the front view for the notch, and we need them in the side view over here. So, I think the key to drawing multi-views for things like this is to break these down into their features. And, so if I look at just that stadium slot as a feature and just focus on drawing it first, and then I draw the second stadium feature, and then I figure out where my center lines go, and then I focus on the slot that runs all the way through. So just breaking it into those parts makes this easier to visualize. This guy looks harder than it is. It's not really very hard, I don't think. You would want to have a gap right here where that center line goes, is lined up with that visible line. There should be a gap right there where the center line hits, but I kind of lost the definition on that. All right. Okay, so over here, here's the tricky part. Let's see how y'all did. You have a hole that goes all the way through the part, and it intersects on an inclined plane on both sides. And because of that, when you see it in the top view, you wind up with an elliptical shape up here in your hidden lines. All right, and I think that's the first time we've had to deal with that. So here's how you figure out the size of the ellipse. First off, the ellipse, it's 1 unit wide because the hole is 1 unit wide. So that's how wide it is on the y-axis. But to know where the ellipse begins and ends, you would project from where the hole intersects on the inclined plane and project up. And right there would be the top of the ellipse. And then you would go to where the ellipse hits the inclined plane down here. I'm doing a bad job of sketching with my mouse today. But you would project up right to there. And then you would sketch that elliptical shape in there and do that on the opposite side as well. Okay. Now, one of the things I want to point out about this object, if we were drawing this in CAD, we have a command called mirror. And so you have an object that's symmetrical along its center line. So if you imagine that this is the center of that part and that this is the center of that part, it's the same on this side as it is on this side, and the same way up here. It's the same on both sides. So what we would do in AutoCAD is we would just draw half of that, and then we have a command called mirror, and we would mirror that over to the opposite side, and that would make that go a lot faster. So you'll see that as we get into the AutoCAD assignments. All right, this guy, I don't think this is too difficult if you get the basic shape and the front view correct. I think everything kind of makes sense on this one. So I'm not going to spend a lot of time with that. You have the solutions. If you feel like you don't have it, you can always go back and look at the solutions in Blackboard. All right, so here we have two stadiums, two stadii, and they're intersecting each other. So we have a slot that goes all the way through. Now this one is trickier. So if you look in the front view, you have a short visible line here and here in the front view, and that represents this edge and this edge right here in the front view. And so you have your center line should have a gap. Where your center line comes out, there should be a gap. The center line should not run into that visible line, and then you should have another gap and then have your center line come out over here, and you're going to do that on both sides. And so when you project that up to the top view, that line will be visible to here, and then it goes underneath this and it becomes hidden back under there, so you need a hidden line under there. Okay. And over here in the side view, there should be a gap right there because you have a visible line, and then that kind of goes collinear with a center line. We should separate those two. All right, this is probably the hardest one on sheet 2.5, and the reason is this rectangular cutout right here. So when you run this hidden line through that you have right here, and you run it through right there, that defines what you see in the top view. And so if you go to this intersection where that hidden line intersects with this arc, and you project straight up, get my mouse to work, sorry about that, that line right there is where that projects up, and it does the same thing on the opposite side over here. So that's your visible cutout, is right there. Most students think that this line here is collinear with this line here. They think this and this line up, so they don't inset that cutout a little bit, but it's actually going to be inset just a little bit. And then you, of course, have the slot going the rest of the way through. So, did y'all do okay on that? You saw that one? Okay, good. Somebody's giving me a thumbs up. At least somebody got it right. That's good. You know, the thing in class, if we were doing these in class, I would have you be putting these on the board, and we would be critiquing them, and so I could really check and see if everybody got them right or not. But here I kind of have to trust you guys. But that's okay. You know, later on when I start grading, if you made a mistake like that and you didn't get that in the right place, I would mark that up pretty heavily. So, you know, eventually you're going to get checked on these when we start handing stuff in for grades. All right, so this is 2.6, and I don't think there's anything that difficult really on this one. This is actually a center line right here. This one has an oblique plane on it right here, but again, if you kind of find the endpoints and connect the dots, then you'll be able to figure out where that goes. And everything else, I think those are all inclined planes. So, you know, so this is an inclined plane. And I said, you know, one of the things that makes an inclined plane is that we see it in its edge view. So here's the edge view of that inclined plane right there. This is an inclined plane. We see it in the front view. So it's in a regular view. We see it as an edge view there. And so anyway, where this oblique plane, which is here, and here, and here, we never see it in an edge view in the normal views. All right, this is a hard one. Let's see how many of you got this. So here's what's happening here. In fact, let me back up one slide and just get it to this. So what we have happening here is we have a large cylinder, which is this guy right here, being intersected by a smaller cylinder right here, and then we have another cylinder that's also being intersected by a smaller cylinder right here. And one of the things that we know is that when two cylinders intersect and they're not the same diameter, that the result is what we call a saddle. So there's a saddle right there. See how that loops in a little bit, and this is a saddle over here, and you've got the same thing on the opposite side. So when you draw that, you draw your larger circle, your smaller circle right there, and then you draw this guy running all the way through. What happens is if you go over here and you see where that hidden line hits versus where the edge of the cylinder is, the cylinder is actually in line right there with that grid. But you go from where the hidden line begins, and it's going to be inset just a little bit to right there. And so there's a little dip right in there. And then the same thing over here, you project up, and you project up from this point here, and that's where you get that saddle in that view. and then it mirrors to the other side. You would do the same thing over here. Okay. Most students don't get that right their first time out. Okay. So the point is that I want you guys to think about whenever you see a project where you have two cylinders meeting each other, whether they're holes, a hole going through a regular cylinder, or two cylinders coming together, that if they're not the same diameter, you're going to have a saddle. And so you've got to think about, well, where's the saddle going to be when you make your multi-view of it? Now, if you have two cylinders and they're the same size and they intersect, instead of a saddle, you get a V. And so we'll see that. Not here, but we will see it in one of the next ones. This one you have to watch out for. You have a center for the end of the stadium right here, and then you have a center mark for a filleted corner that you have right there. And of course, you have that on the top, so you need to show two center marks on this guy. And as I said, if anybody has a question, feel free to unmute. I'm going to check the chat, so nobody's put anything in chat either. All right. So this one's really not too difficult if you get those center marks in there, I think, and it's just because it's two different sizes and diameters. And then when you come over here, you have a radius right in here, and that radius is actually 1.5. And so if you measure from this corner, you want to come up 1.5 and put your center mark in there, and then extend your center lines out in this direction and find where that is. Okay. Now on this one, we don't see a visible line anywhere in here, you know, because this guy blends all the way. It never drops straight down and creates a plane. If it did drop straight down, we had a plane, we would have a visible line. Okay, so this is where we have two cylinders that are the same diameter coming together. So we have this cylinder here intersecting this cylinder here, right? And they are the same diameter, and so what we wind up with is right in here, we wind up with a V where those two come together. But right in here, we're going to have actually it's up here, we have that small saddle where those two guys come together up there. Okay, so when we draw that, it's the side views where things get tricky, right? And so if we project across from where the hidden line intersects right there, that tells us where the bottom of the saddle is over here. But then we have this hole intersecting this hole, which are the same diameter. So when we project those across, we want to go to that corner and draw a hidden line to the opposite corner and go from this corner across like that. So just remember, when they're the same size, it's going to be a V or an X, and when they're not, it's going to be a saddle. This one is pretty simple. You do want to extend the center line out here 1/4 inch, because this center point is the center of this arc as well as this guy. But down here, you only need to extend out 1/4 inch because it's only the center of this and that view down there. This guy has a little bit of tricky stuff, and one of the things is, as this arc comes around right here, it doesn't make it all the way to that grid line right there. It's sitting up just a little bit. So you want to project from that intersection right there across. And so this line that you have right here, mine doesn't show up very well, but it should be just up just a little bit above the grid line over there. And I think get all your hidden lines in the top view if you know where those are coming from, right? And then you're getting hidden lines from all these points down here up into the top view. Okay, this one is a tough one. Most students don't get this the first time they try it. So the front view is okay. The side view, it's the hidden lines that fool most people. So you're going to have a hidden line right there for that plane. So you have that, and that goes in too, and then it goes straight up, and it's hidden when it goes straight up until it gets to this edge right there. And then from there it emerges as a visible line. Then you have the same thing on the opposite side of that. You have a visible line here going into a hidden line, and then a flat plane coming across that's hidden from you that also goes up as a hidden line till it gets to that horizontal line and then comes out as a visible line that's vertical. And then the same thing's happening here. When you look down on this top view, you're going to have a hidden edge, which represents that vertical edge right there. And then it comes across like that, where it's hidden, and then it emerges and becomes visible. And it does the same thing back in here. And of course, these hidden lines are the hole that goes all the way through. Okay. So, I think the thing that you want to sort of visualize is that, in the real world, you're out there on a job and this thing doesn't exist yet. That's the whole point of why you're drawing it. And so you're really going to be using your imaginations to figure, to kind of conceive of what these things look like. And that's one of the things I think that's really great about being a designer, is getting to think stuff up and visualize it in your head before you draw it or design it. And not many jobs that you get to do stuff like that anymore. All right, so this is the last one, and this is also a tough one. So front view's not too bad, right? But it's the side view and the top view that have a couple of tricky things. And so let's go right here to this vertical line that you have. And you can see it comes up, and where it intersects this circle, it projects across. Let's see, that one is coming to right here. And then we have this line right here that is going up a little bit higher and becoming tangent. That comes to the top of this guy over here. So the point is that that line right there, which represents this plane right there, does not make it all the way to the top. You can see it runs up and then it blends in before it makes it to the top, and it does the same thing down here. And as a result, when we bring this down to where the tangency point would be and project across, that tells us where the end of that is. And then this visible line here and this visible line there, those come from across from where this vertical line here meets and comes in right there. Right, so that one is one that not everybody gets right the first time they look at that. Now, in the top view, we see this inclined plane that we have right here, and the inclined plane is running up, and you can see this edge that it's giving us right here blends in, and so we have a visible line that's coming across, but then it ends and it blends in. So where does it end? Well, we go to the front view and we follow it all the way until we get to where it goes tangent. So where this line touches this circle at one point where they meet, we project up, and that's where the run out ends. And we do the same thing on the opposite side. So we run this up until we find the tangent, project straight up, and that's where this run out hits right there. And in the parts that we're going to draw with AutoCAD in the next couple of classes, we're going to have a situation like this where we have an inclined plane running up onto a cylinder, and you're going to have to end that run out, and so you'll need to project from the tangent point in the front view up to the top view and over to the side views to figure it out. Okay. Well, that's the end of the sketching part. Everybody's probably, yay, now we're done with that. We can go on just to CAD. So, and that's right. We're going to get out of this thing. And let me close this down for a second. Oh, actually, I want to just switch my... All right, so in chapter 3, which is the traditional drawing chapter that we normally do if we were face-to-face, we would do that. We'd have some drafting tables. We'd work on this in class for a couple of class sessions. But since we're not going to do it, it actually kind of helps us out in the online course because we gain that time to work on like the capstone project and things later in the semester. So we're going to gain a little bit of time because of not doing chapter 3. But I do want to point out a couple of things that are in that chapter that are important. And one of them is sheet sizes. Okay, so I think we talked about this the other day, that a mechanical sheet size is 8.5 by 11 inches. And if you can remember that that's the size of an A size sheet, then what you imagine is if you take one A size and you put it right next to another A size, and if you could join that into one sheet, that would make a B size sheet. Okay. Now, as I said, all of this is in chapter 3 of your book, so you can look this stuff up. But you know, the main thing is just remember what an A size sheet is. So it's pretty much printer paper. You know, the size of a printer paper. You put two of them side by side, that turns into a B. And then if you took two B's and you put them side by side and joined them together, you would have a C. And if you took another C size sheet and joined it together, that would yield a D size sheet. And two D's make an E, and so on like that. And so sheet sizes just keep getting larger up to a point till they get unmanageable. But it's important that you know this, because if you're on a job, the boss may say, I want you to print that on a C size sheet. And you're supposed to know what they're talking about. Okay, so that's why. So if you can remember the A, because it's real common, then you should do okay. Now, one thing that kind of complicates this, these are mechanical sheet sizes. And mechanical sheet sizes are controlled or kind of defined by an ASME, American Society of Mechanical Engineers standard. It's Y14.1-2005. Now, all that's in your book, and so you could always look this up. But I just want to point out that we're not just making this up. There is an ASME standard out there that kind of defines this. But here's where things get a little bit confusing. Mechanical sheet sizes say that an A is 8.5 by 11. But when we go to architectural sheet sizes, they say an A size sheet is 12 by 9. Now, even though they say that, in most offices, your printers just print 8.5 by 11, so most architectural firms are still printing their drafts 8.5 by 11 and not 12 by 9. But you can see that a B size sheet's a little bit larger, a C is a little bit larger, and a D is a little bit larger. That's because they start with a larger A size sheet, but they're still joining them together and getting that larger size. All right. So back in the day, you drew on something called vellum, which was a paper that would allow light to pass through it pretty easily. And that's what people use to make blueprints or blue line prints. Nowadays, most companies they run more of a Xerox copy type print when they send those out to a job site. And so I want to just point out something. So there is a place here in town called Miller Blueprint. And So if you had an architectural firm and you needed to send out 20 sets of drawings for a house or for a building, you could send your digital file to Miller Blueprint, and they would run those 20 sets for you. And they even have a guy who's a delivery guy who'll take them out to the job sites and drop them off for all the contractors and everything. There's another place in town called Burke's, and Burke's is called Burke's Reprographics. And Burke's business is pretty much the same way. You send an AutoCAD file to them and tell them how many copies you need, and they will print it for you and bill you. Okay. So just keep those guys in mind, because you're going to probably dealing with those in your career. If you live in Austin, every place probably has several, reprographic companies. Now, when you're drawing in the metric system, an A size sheet is 297 millimeters by 210 millimeters. All right. So when you think of that 8.5 by 11, pretty much if you converted that to millimeters, you would be looking at approximately 297 by 210. And I wanted to point out something. The ASME has a standard for that, for metric drawing, and it's the exact same number as the other standard, except they add the letter M, which indicates it's a metric standard. Okay, so I'm going to skip through this stuff because we're not going to do these, but they are in your book, and they're also in the chapter 3, but there is something I want to get into here. So, scaling. And so what does it mean when we say we're going to draw something full scale? Well, what it means is that the size of the object in the drawing is the same size of the object after it is manufactured. That's what full scale is. So you draw it the same size it's going to be when it's manufactured. So when we put this in a drawing, we write a scale on our drawing. And a full scale drawing, you would say that your scale is 1 equals 1, because 1 unit on the drawing equals 1 unit after it's manufactured. Okay, so that's what full scale is. Sometimes people write it 1/1, they'll write it 1:1, but it's really just a ratio of 1 to 1. So that's what full scale is. Now, a half scale drawing means this, that the size of the object in the drawing is half the size of the object after it is manufactured. Okay, and so usually if you have a big part and it's not going to fit on your sheet, you draw it half size, and then it will fit on the sheet. And so how you notate that on the drawing, you say that the scale is 1 equals 2. And if you look at that 1 equals 2, and you imagine that the equal sign replaced with a slash, it's half scale. So that's how you can remember full scale was 1 equals 1. So you can imagine it is a fraction of 1 over 1. 1 will go into 1 times. 2 will go into 1 0.5 times. So your drawing is half scale. You multiply everything times 0.5 when you draw it. Now when you put your dimensions on there, even though you drew it half scale, you put the full size dimensions on it because you want it built full size. Okay, you don't cut the dimensions in half that you put onto the drawing. They have to be full size. All right, so let's look at double scale. So this time we have a part that's very small, and if we drew it full size, it would be too small to put dimensions on it. So we could double everything. So in this case, the drawing is twice the size of the object after it's manufactured. So that's 2x. And so the way you would write that scale is 2 equals 1. And if you write 2 over 1, 1 would go into 2 times. So your scale is 2x. Okay. So this is double scale. This is half scale. And so that's why I think it's important to just remember, make it a fraction. and then you can tell what your scale should be on that. So on every drawing that we make, you'll be writing a scale. Once we start doing this in CAD, there will be a title block in the lower right hand corner of each sheet, and we'll be putting in a drawing scale for everything. All right. So I'm not going to get too far into this because we're going to come back to this in Chapter 5, but we have the several different types of scales that we find in engineering and architectural offices. This is called an engineer scale. Engineer scale has these whole numbers like 10, 20, 30, 40 on it. And so when you pick up a three-sided scale that looks like this in an office, I just happen to have one right here, but there are different scales. There's an engineer scale, there's a metric scale, and on that one, your increments are generally in millimeters, though they could be interpreted as centimeters or meters. So there's a metric scale. So if you were in an office, let's say you were in Europe, you would almost certainly be using a metric scale. And then you have an architect scale. And what the architect scale, it has fractions on the side. And so you can see this, it's upside down because that's the way that orients, but it says 1/4. What that scale means is that 1/4 inch equals 1 foot 0 inches. So that's what the scale would be for a drawing that you could measure using this scale right down here. And most of the drawings that we print, or when we print them for that are architectural, we're going to print them either 1/4 inch equals 1 foot. We may print them 1/8 inch equals 1 foot, or we could even print them 3/16 of an inch equals 1 foot. So the point is that in AutoCAD, we actually draw everything full scale all the time, but when we print it is when we scale it down. All right. So that's where when we print something, even if we draw it 1:1, we may print it half scale. We may print it 1/4 scale or something like that. So in AutoCAD, we never scale stuff down when we draw it. We draw everything to the full size, and the scaling occurs when we send it to the printer. So we'll have to get into that when we start printing things. So I just want to point out the two things about the engineering scale. So here we have the engineer's 10 scale, and each increment on the engineer's 10 scale is 1/10 of an inch. Or you could think of it like that, 1/10 of an inch. Okay. So if we go over to here, we're at 1 inch, and then we count 5 more increments, then that would mean that this dimension between the 0 and that mark right there would be 1.5 inches. And here we have 2.750 inches, so we've got a dimension hitting right over here. And here we have 3.125, and that's hitting over here. So I'm going to show you in the next slide a little bit more about that. So here we have a dimension, and it goes to 3 decimal places. So the first place is whole inches. Okay. Then we have our decimal point, and then we have a placeholder here that's for tenths of an inch. And then we have a second placeholder that represents hundredths of an inch. And we have a third placeholder that represents thousandths of an inch. Right? And so if you were talking with a machinist, and that machinist was looking at that dimension right there, they would say that that dimension is 3 125 thousandths of an inch. Does that make sense? Because see, they counted all the way over to the third place of precision. So 3 125 thousandths of an inch, because that's really what that is. Now, if you didn't have the 0.25 on there, this would just be 3.1, which would mean it's just 3 1/10 of an inch. If you didn't have the 5 on there and you just had the 0.12, this would be 3 1200ths of an inch. But if you have 3 places and you're into thousandths, you could even go into 10 thousandths of an inch and so on like that. It would cost you a fortune to manufacture parts that were measured to 10 thousandths of an inch. But anyway, so we're going to come back to this. when we get into chapter 5. But you're going to start making measurements on drawings. You're going to be using dimensions as you make these drawings starting today. And you're going to be looking at dimensions that may go to 1 decimal place, 2 places, or 3 decimal places. So I want to point that out to you as you start working on these next drawings. All right, so I'm going to skip through all this because I'll come back and talk about all this stuff later in chapter 5. So in fact, I can get out of this PowerPoint right here. And so I wanted to show you a little bit about AutoCAD today. So I'm going to open up AutoCAD and drag it over here. So hopefully you guys are seeing AutoCAD right now. Is that true? Yeah, good.